Yeah, that's it. Okay, so what I've done is I spent a couple of nights doing this. All right, so let's have a look at some of these questions, shall we? I didn't do all of the questions. I tried to, again, not bother doing repeats. There's a whole bunch that are a repeat of the same thing. So have a look at this. What I've done here is, this is example one. The question asks, now, ideally, you should not look at this part of the video until you've attempted the questions yourself first, okay? Because they're really obvious when somebody points at the answer, okay? But when you're looking at them fresh for the first time and saying to yourself, oh, I wonder if I could do that myself, you know, often it's a different story. So switch off now, go have a crack at the questions. You can't do a question, look at the solution. The solution is kind of not detailed enough. Come to this document and have a look. And this document's going to be on Compass and it's going to be on OneNote as well. All right, so as usual, okay? But if you are interested in having a look at the first few questions with me, here is my my advice on how to approach a question. Okay, first thing, read the question. All right, make sure you read it carefully. The figure shows a small DC electric motor powered by a battery. When they say battery, they are implying a direct current because a battery just has the same sort of load the whole time in the same direction. Okay, that's the essential difference between AC in the PowerPoint. I pointed at PowerPoint, you can't see, it's over there. And the difference between a PowerPoint and a battery. All right, so it's a DC power supply for a DC motor, so everything's nice and normal, as expected. Okay, nice and basic. Okay, through a split ring commutator, there it is. There's a split through the middle that you can see. The magnetic field between the poles of the magnet is uniform. All right, they say all the rules. Okay, so what I do is, this is the current. The current is, there's a switch here that's shown that's open. So the current is switched on and the coil is stationary in the position shown above. That's ideal. In that position, you would expect it to move. Which of the following statements best describes the motion of the coil when current is switched on? You may assume that any frictional forces opposing rotation are very low or insignificant. Okay? Now, which way is it going to turn? They've given you a reference. Alright, so obviously as viewed from the commutator end, it's either going to spin clockwise or anti-clockwise. You just got to decide which one, right? Okay, so the first thing you do, what's the direction of the current? It gives you the positive terminal, you know it goes positive to negative. So I put my little blue arrows through my wire telling me which way the current is going, okay? Because I'm going to need my right-hand rule at some point, alright? Now, to not confuse myself, I chuck in my magnetic field lines, and my orange lines there. Alright? Magnetic field lines that way, wire going through there. As usual, what I do is I focus on one length of wire. I don't try and look at the whole loop because it makes it too confusing. I take my right hand rule, aim my thumb in the direction. I'm going to focus on JK rather than LM. And I'm going to do that. My hand lines up the field, and there's a force down on JK. If there's a force down on JK, I can assume there's a force up on LM. So my loop does that, which is in the direction of B. So, bam, the coil will rotate in direction B, shown above. I'll explain there as well. Alright, so that's the process of deciding. Getting to the point where you use the right-hand rule is, it's important to make sure you know where everything else is before you do that, okay? So let's see, over here, there's a coil of wire that is free to spin, is placed between two. Now notice here, they haven't drawn slip rings, they haven't drawn a commutator, they haven't drawn anything. So that could be the point of the question, all right? They've also tried to make it look complicated by chucking an angle in here. Very rarely will you ever see angles actually used in this in any real way, in any significantly difficult way, I guess. Significantly difficult. Anyway. So, the coil of wire is free to spin, okay? X is connected to the positive terminal. So, X is the top line, and Y is obviously connected to the negative terminal. Alright, so X is connected to the positive on the power supply, Y is connected to the negative terminal. The coil is set in the position shown and viewed from from the front near X and Y, so viewed from here, which of the following will occur when the power supply is turned on? So you look at this wire, right? You can see the force will be either up or down, but a component, because it's skewed at 20 degrees. Because it's skewed at 20 degrees, a component of that force will be in the direction that will make it move, all right? Which direction? So, okay, I'm going to line up. I put my arrows in as usual, and I put my field in as usual, so I don't stuff this up. Line it up. It's like, oh, okay, there's a force down on this wire that I've highlighted in orange, okay? There's a force down if I line it up with my right-hand rule. Okay, so if it's a force down, it's going to try and go all the way down. But what's actually going to happen? Let's look at the different options. The coil will rotate continuously in an anti-clockwise direction. Well, anti-clockwise, it's actually, if it moves this way, if I look at my clock, that's actually clockwise. So, firstly, no, it's not going to rotate. It doesn't say there's a commutator. It's actually going to move clockwise, not anti-clockwise. So it's just wrong in every way. The coil will rotate continuously in a clockwise direction. Again, it's not going to rotate continuously because there is no mention of a commutator being used here in what is clearly a DC situation. The coil will rotate anti-clockwise and stop 20 degrees from where it started. Why? Why would it do that? Okay. D. The coil will rotate clockwise and stop 160 degrees from where it started. Okay, 160 degrees means that this wire here will have moved all the way down to 180 degrees. Much like what I said earlier, that if you don't have a commutator fitted, what will happen is the wire will wobble, and then just frictional forces over time will eventually stop in the middle, okay? Because the forces are equal on, both sides. All right, so the coil will rotate clockwise and stop 160 degrees from where it started. That's why that orange line you would imagine vertically all the way right down to the bottom. All right, so that's what, using the right-hand rule, a nice little basic question there. This question, same as above. This one, this is just the same idea, okay, but in a different setup. Rather than a spinning wire, you've got a rail here. Basically, two metal bars connected to a power supply that is DC. The current is running, you can see from the arrows, out this way, and they're not connected to each other. The whole setup is immersed in a magnetic field, which is produced by something, either a solenoid or a permanent magnet. And you can see the field lines are coming right out here. All right, that's what the dots mean. Which way will this bar is metal and it connects to both of these rails that are alive, okay? So bang, it touches there. Which way will the bar push, okay? Line up the direction of the current with the direction of the field. See, right at me, okay? So which way is the force? That way, okay? So the bar magnet moves, the bar moves to the right. Okay, easy. That's a simple one, but just went through it because it's a weird setup that you may not have seen before. Probably haven't. Okay. Again here, a spinny thing. There's a really good. Again, you would look at what I've done here is I've looked at the direction of the current through the loop, which is given. A little hard to see black arrow there, so I made it more obvious. Tried it on this one, tried the right-hand rule on this one, okay, did not give the answer that's required. In which direction does the coil begin to move? In other words, which way does it spin? Does it spin this way, that way, or does it all just move this way or move that way? All right? If you use your right-hand rule appropriately, you get that spin, okay? And that's just you lining up the field with, there's the direction of the field, B, magnetic field, direction of the current. There'll be a push on this arm, which means there'll be a push this way on that arm so that it should spin that way. All right, easy question. Another easy one. Okay, now, I went to, notice how much writing I did here. And that is basically to make sure you understood the difference between the direction of the force on the wire and how the torque changes through the rotation on the loop. Okay, so another big explanation there as well, all right? And that's all on the help sheet now, all right? Over here, this one can be a little bit confusing, and I remember the first time I saw this question, I think a couple of years ago, you have to really get your head around what these diagrams actually were about. There's not a terribly old question. It's about 10 years old. Like, to me, that's not really a long time. What you're looking at here are, there's a power supply connecting a wire here that then creates a solenoid, all right? Then that same wire comes out of the solenoid, jumps over this wire, and connects to this side of your commutator. Now, it's because it's some photocopy of a photocopy, you can't really see it very well, but there's a diagram. You'll see it in your copy that commutators are clearly fitted to all of these, and these are the brushes that keep the connection. All right. Anyway, so it's asking in which circuit will the rotor turn in a clockwise direction. So what's really important here is you've got to kind of use a couple of different rules. You're going to use your right-hand rule, absolutely, but you can't use your right-hand rule until you know the direction of the magnetic field. And don't forget, as of the last topic, the magnetic field is in the magnetic field is set by these solenoids. Now, here's one, just to remind you, here's one I made earlier, okay? So, what I've got here is a jar with a wire wrapped around it. You can see the wire comes out the front here and goes out the back here. So, how do you decide which end of this magnet here, of this solenoid, is going to be north and which one's going to be south? The way you do it is you look at this wire, as it goes in, connected to the positive terminal, it goes that way, which means it hits the front face of this block of metal and goes straight up, and then goes around, around, around. So you can actually follow that and see, and put your arrows in along the wire, telling you which way the current is moving through the solenoid. Here's your solenoid, okay? So if I try to align that one, the way this one is, let's see, well, it's kind of opposite, doesn't matter. The idea is that if the current comes in, if this is connected to the positive terminal, okay, then in this orientation when you're looking at it this way, you'll see that the current comes in through here and is moving in this direction to you down, okay? You put your north finding rule with your fingers in that direction, so that means it points north. That's the north end, okay? Now it doesn't matter if I roll my hand all the way around so that in my point of view, my reference frame, that the current is moving up. For you it's moving down, for me it's moving up. It doesn't matter. For me it's moving up. I still put my fingers in the direction that it's moving. My thumb still points north. North doesn't change because I'm sitting on this side of the solenoid and you're sitting on that side, okay? So it's still, that's north no matter what, all right? Okay, if I flip it around and the current is now moving up for you and down for me, well, again, in your orientation, in mine, that's north, okay? So, if you get that, this is really easy, all right? If the current's moving that direction, that's the north end, that's the south end, so I stuck an S there. I follow, this line is connected to the negative terminal, okay? So for it to be connected to the negative terminal, I know that it eventually needs to come out and enter this way, which means it needed to go in this way, which means it goes up that way, putting a north end on this side and a south end on that side. Now, this is actually pretty good, except that when you line up your right-hand rule, it causes this loop to spin anti-clockwise, which is not what the question was. The question was clockwise, not anti-clockwise. So I had to look for another version that just went the other way. And in this case, it basically connected the terminals around the other way. And this version gives me a south end on this side and a north end on this side, which then gives me the force in the correct direction to give me a clockwise rotation on this loop. All right? These two are just completely off because you've got south ends on both of those, which won't lead to anything. All right? Okay. Now, let's see. Was there anything else that was even remotely interesting? All right, I've got a lot of writing here. Okay, so in this question, in the motor shown, so it's another DC motor, the rotor spins clockwise. So you can actually confirm that. Does it spin clockwise as viewed from the commutator end? Well, that's the current that way, which pushing down this way, this pushes up that way, so it's doing this, which is clockwise, okay, from this end. Cool, you're not lying, that's great. All right. When connected to a DC power supply, so yes, beautiful, all right? So this is exactly the same situation that was illustrated in the previous question with solenoids being used to create the magnetic field, all right? What happens to the motor when the motor is connected to an AC supply? Okay, so it's connected to an AC supply, and you know, if it connects to an AC supply with a commutator, you're going to say to yourself, well, what happens? Does it spin? Does it wobble? What exactly happens? Well, this is where you've got to put your logic brain on, okay? All right, so if you connect it to an AC power supply, through the solenoids, you get a constant flipping, okay? Because every half cycle, the current runs the other way, all right? So what will happen is you'll get a north here, then a south here, then a north here, then a south here, then a north here, then a south here, okay? Over here, its buddy is going to flip to the opposite of this one's doing, so it's just going to be doing this constant flipping as the current moves through, right? And you're like, well, how's the commutator going to affect this? Well, what does the commutator do? It changes the direction through the loop every half turn. You say, but it's already changing, right? Once you flick to AC current, it's already changing every half cycle through the loop. So chucking a commutator in there, what does that do? So it's changing every half, but then the commutator kind of changes it back. So what does that actually mean? Have you thought about it? It means that while these are constantly changing polarity, the current through the loop stays in the same direction the whole time, okay? So basically, it's the reverse of what the commutator does with a DC power supply. In a DC power supply, the field stays the same because these are permanent magnets, that never changes, but the current keeps changing direction. This version, the poles keep changing, but the current stays in the same direction, right? So it means it spins. It does spin, but it'll only spin at the frequency of the AC power supply, which then leads us down to why you lose sort of control over how much or what you can do with it. And that's what all of that purple writing tells you about, okay? Basically goes through it. All right? So, yeah, the commutator, which ordinarily changes the direction through the loop every half turn, kinda has the opposite effect when you're using AC by keeping the current through the loop in the same direction the whole time. Really tricky idea there. All right. Okay, what's next? Torque question. All right, that's not hard. That's easy. That question's same as above. This question can be confusing because it doesn't ask for the magnitude of the force. It doesn't ask for the magnitude of the torque. All it says is direction. That's it. So what's the direction, all right? So you know that the force with a commutator attached, that the direction of the force flips every half turn, okay? But the direction of the torque remains constant. Now I know the magnitude doesn't for torque, but the direction does, and that's the point. That's why it keeps spinning. All right. So that's a good question to keep in mind. Okay, compare the forces acting. Oh, all right. Okay. A metal loop is connected to a battery and placed in a uniform magnetic field. Current flows through the loop in the direction shown. And the loop is then allowed to rotate by 90 degrees about the axis PQ. Compare the forces acting on WX and XY before and after this rotation. All right, so I've written there that Colin's notes are, the solutions are, it's fine. There's nothing hard to understand in this one. When you're looking at WX and XY, in this orientation, WX experiences a force down, so maximum force down that it will experience, or, oh well, not maximum, maximum rotation. So WX experiences a force down. What about XY? Let's see, XY. Try and line up, this is a good little exercise, try to line up the direction of the field with the current for this line here. It's impossible. You have to change the rule to make it line up, and you can't do that. So if the rule does not line up, it just means that the force is zero. And that means, you've got to imagine that that is quite reasonable, because the line, the direction of the current is moving with the magnetic field, okay? They are parallel to each other, all right? That is one of the rules that tells us that there's not going to be a force, all right? Now, rotate this into the vertical position, all right? In the vertical position, the force on WX is now completely out, like towards you, if we're looking at the loop in this direction. But what about XY? XY now looks like it is perpendicular to the field. So, what happens to the force on the XY in the vertical position? Well, it will be, if I rotate this way, then the wire XY will be moving down into the page. Its current will be moving, you'll be down, so you'll be moving, if it's down, you're looking at sort of a field, or, you know, basically in the current, it's moving away from you. Alright? So there's the wire heading straight into the board. Now, can you line up the wire with the direction of the field? Well, yeah, you can. Notice, thumb in, north to south field. So which way is the force acting? Well, in. Alright? So if I've done that right, that should be consistent with whatever Colin wrote in his solution there. Alright? Okay. So yeah, alright. Anything else that's, no, that's another basic question. The wording is, okay. Explain the role of the commutator in the operation of the motor. Again, always go to the help sheet, version, because it's worded very carefully to make sure that you get it right, okay? Yeah, see orange arrow, because that orange arrow belongs to this question here, question 16. Question 17, just an application of Nibble, okay? Force equals NIBL, all right? The coil's position only matters when it is vertical, where the connectors lose contact with the commutator for an instant. That's it. Okay, so that gives you the force on there. Again, this is just another standard question. Again, here, what is the magnitude on acting on UV, which is from here to here? Okay, from here to here, it's running parallel, so the force is zero. That's that question here. Explain the purpose of the split ring commutator. Again, that's the help sheet. Over here, yeah, that's basic. You do that easily. That's this question over again here. Explain your answer. Oh, okay. One of the last things I'll tell you is when you're explaining an answer, is it like why does this happen? In physics terms, well, why do magnetic fields act on electric charges? I don't know. It's a quirk of nature, all right? It happens, all right? Tons of really, maybe science again, is done to try and figure out why these things happen. No one's actually asking you to explain why a charge is acted upon by a magnetic field. In the context of high school physics, why is answered by, well, because the current moves in a particular direction, the Y will have a force acting on it as per the right-hand rule. That's your Y, okay? That's all you need. So if you look at this particular question, don't expect that you're really asked to go into any significant detail about why these things happen. The motor is initially stationary as shown above. In which direction, clockwise or anti-clockwise, will the motor rotate when the switch is closed? Explain your answer. Okay, this is a standard explanation. When the switch is closed, current will run from J to K. So you explain what's happening. When you close the switch, what happened? Well, the current flows. Why? Because it does. All right. As the loop is inside a magnetic field moving from north to south as indicated in the diagram, the wire segment JK will experience a force down by the right-hand rule. This will cause the loop to spin anti-clockwise. That's why, all right? You don't need to go into any more depth than that or any heavier science than that, okay? That's the kind of stuff that you end up learning once you leave here and really get into the physics, okay? This is just the very beginning, all right? N is not always 1, okay? You've got to look out for things like this, 50-turn coil. So N is 50. You cannot leave that out. And the other thing that someone, at least one person will do, all right, in a SAC or the exam, is you're going to take the, let's see, this value here. They're being kind to you in this question. It's in meters, all right? If it's in meters, then you just apply it. Most questions will have it in centimeters. That's a 5 centimeter length or a 40 centimeter length, whatever it is. It's going to be in centimeters or millimeters, okay? And someone, I know, happens every time, is going to forget to convert it to meters. You must convert it to meters or your answer is not in the right scale, all right? So please don't forget that. Anything else? Yep, that's it. Can you believe it? Done already. How much fun was that? Okay, so it's only a very short chapter, but don't worry, the next one makes up for it with another like 70 or 80 questions, but we'll leave that for later in the week, okay? So have fun with that. Don't forget, always plenty of opportunity to talk to me or email me or text me or any of that for any extra help that you need. If any of that didn't make sense, all right? Yeah, bye for now.